Rational Functions Part 3, Horizontal Asymptotes. Recall that a vertical asymptote occurs at the x values where y goes to infinity, or negative infinity. A horizontal asymptote is the y value when x goes to infinity, or negative infinity. So vertical asymptotes, y goes to infinity. Horizontal asymptote, x goes to infinity. Now there are functions that have more than one horizontal asymptote. As a general rule, when I'm teaching college algebra, I don't worry about those cases. So the horizontal asymptote that occurs when x goes to infinity, for us, will be the same horizontal asymptote when x goes to negative infinity. A note that sometimes bothers students: a graph cannot cross a vertical asymptote. It is a discontinuity. It is what we call an infinite discontinuity. I basically have to go to infinity to cross over the asymptote. But a graph can cross a horizontal asymptote. Now, we draw the horizontal asymptote everywhere. I'll show you just kind of a quick sketch. Let's do a vertical asymptote first, and then maybe a horizontal asymptote. And so we see the horizontal asymptote when we graph things. But the horizontal asymptote is really way, way out at the end of the graph when x goes to infinity. So it doesn't belong here near the center of the graph or any finite values. We just draw that to help us see what's going on, and when we want to draw a graph by hand. But let's talk about horizontal asymptotes for a little bit. When do they occur, if they indeed do occur? And are there any shortcuts? Now, a lot of times, horizontal asymptotes are taught in three pieces. That is, sometimes say bigger on bottom, bigger on top, something same in the middle. I don't teach it like that. Not saying it's a bad way that they teach it. I'm just saying I teach one way that if you understand this one way, it works for every circumstance. Let's do one example, the correct mathematical way. But I don't want to do the correct mathematical way after this. I want to use the correct mathematical way to find a shortcut. Now, the horizontal asymptote occurs when x goes to infinity. So what I'm going to do is I'm going to start, before I let x go to infinity, I'm going to factor out the highest power in the top. That is the highest power in the numerator and the highest power in the denominator. So the highest power in the top is x squared. So if I pull that out, I get 1 minus, and if I factor the x squared out of the 5x, I get 5 over x. Convince yourself you get this. If I were to distribute this back out, x squared times negative 5 over x, I would indeed get negative 5x. And then if I factor out an x squared out of the 2, we get 2 over x squared. Let's do the same thing in the bottom. The highest power in the denominator also happens to be x squared. So if I factor that out, I get 2 plus 3 over x minus 1 over x squared. Now, before I let x equal quote-unquote infinity, do you see what we can do? If you saw that we can cancel out the x squareds, great, because we certainly can. And now I'm going to let x go to infinity. That is, I'm going to pretend that x equals infinity and plug it into each of the terms with an x. In the numerator, I get 1 minus 5 over infinity plus 2 over infinity squared, which is still infinity. In the denominator, we get 2 plus 3 over infinity minus 1 over infinity squared, which is still infinity. Now, what does 5 over infinity equal? Or what does it get really close to? For that matter, what does 2 over infinity or 1 over infinity or any value like 1,000,000 over infinity, what does that get really close to? And my claim is that all of these approach 0. The way I think about it, pretend I had 1 over infinity like I did in the denominator. Imagine that I have $1 and I divide it amongst an infinite number of friends. How much does each friend get? What if I had $100 and I divided it amongst an infinite number of friends? How much would each friend get? It doesn't really matter, right? How many dollars I start with. When I divide it amongst an infinite number of people, each person gets basically nothing. So the only thing left over is a thing that did not have any x's. That is 1/2. So my horizontal asymptote is y equals 1/2. Now, what is the shortcut? Well, the shortcut is that the only thing mattered at infinity, that's the only thing that matters at infinity, are the highest powers. I didn't care about any of that stuff in the end. So when I'm doing horizontal asymptotes, all I look at are the highest powers. That is, in infinity, only the highest powers matter. Let's take a look at another rational function. Let's consider y equals, say, 3x squared plus 10x minus 2 over, let's say, 3 plus 4x minus 2x squared. And we want to find the horizontal asymptote, which I will call HA. I know that the horizontal asymptote will occur, if there is one, when x goes to infinity. I also know that in infinity, the only thing that matters are my highest powers, along with their coefficients. So if I ignore everything else that's not my highest power, I get 3x squared over negative 2x squared. Something really nice happens. My x squareds cancel, leaving me with negative 3/2. So that's my horizontal asymptote. Y equals negative 3/2. What if our powers don't match? That is, what if the highest powers, top and bottom, are different? All right, let's consider this one. Let's consider x squared plus 3 over x cubed plus x squared plus, say, 20. And we want to find the horizontal asymptote, which I am calling HA. I know I can look when x goes to infinity. And if I were to do the long way, the proper mathematical way, I would see that the only thing that really matters are the highest powers, top and bottom. Well, they're different. Does that matter? Well, we can still simplify, can't we? If I simplify, if I divide an x squared out of top and bottom, I'm left with 1 over x. The only difference between this problem and the last problem was, or really the last two problems, after I did the highest powers top and bottom and canceled, I had no x's left over. In this problem, I have an x left over. I have 1 over x, in fact. So there's an extra step. I can simply let x, quote unquote, equal infinity. And I get 1 over infinity. So if there are no x's left over, I don't need to worry about anything. But if there is an x left over, I can imagine x equaling infinity. And what does 1 over infinity get really, really close to? Well, 0. So my asymptote is y equals 0. Now, I'm going to show you an alternate way that my students like. I'd like it as well. It still involves highest powers top and bottom, along with their coefficients. So it's really I had a 1x squared and a 1x cubed. But a lot of my students like to think of my horizontal asymptote like this. They're going to take the highest power. In this case, it's in the denominator, and it's a 1x cubed. And they imagine that the highest power in the numerator also is x cubed. But how many x cubes do you have in the numerator? Well, you have 0x cubed. So my students like to make the highest powers match, and I kind of like it as well. Because what happens here, I can cancel out my x cubes, and I get 0. Let's do another example. And just kind of a side note, when you get used to doing these problems, you can generally just look at the equation that you have and determine the horizontal asymptote without doing any work. But I'm going to continue to go through some of these things. What if I had 3x plus 18 over x squared plus x plus 4? What is the horizontal asymptote, if any? Let's do our highest powers. Okay, the highest power on the bottom is x squared, and it's a 1x squared. The highest power in the numerator is x to the first, but I want to make my powers match. So the highest power, if I call it an x squared, says I have 0x squareds. Canceling out my x squareds, I get 0. So the horizontal asymptote is y equals 0. Or the other way, taking the actual highest powers with their coefficients and then simplifying, I get 3 over x. But since there's an x left over, I pretend x equals infinity. And either way, I get the same answer. How about this one? What if we have y equals, say, 4x cubed plus 7x squared plus 2x over 2x squared plus 3x minus 5. How do we handle this problem? Well, we do it the exact same way. Let's take our highest powers, top and bottom. And I'm going to do it the original way, where I take the actual highest powers along with their coefficients, giving us 4x cubed over 2x squared, because at infinity, the only thing that matters are the highest powers. We can simplify. If I divide an x squared out of the top and bottom, I get 4x over 2, or 2x. If there are no x's left over, we would be done. But since there is an x left over, we imagine that x equals infinity. So we plug in 2 times infinity, that is, we plug in infinity for x, and we get infinity. So the horizontal asymptote is y equals infinity, right? Well, no. If y equals infinity, quote unquote, we say that there is no horizontal asymptote. If we look at it the other way, where the highest power on the top is an x cubed, so we imagine that the highest power in the bottom and the denominator is also x cubed, but there are 0 x cubes, and then divide, we get 4 over 0, which goes to infinity. That is, y goes to infinity, which means there is no horizontal asymptote. However you do it, you should get the same answer. Let me put down 2 quick problems for you. And I want you to determine the horizontal asymptote, if any, of these graphs. And if possible, can you tell just by looking what the horizontal asymptotes will be? Hopefully I gave you enough time to think about this. HA for horizontal asymptote. Did you put y equals, and very specifically y equals, did you put y equals 5/4 for the first one? Taking the highest powers top and bottom, simplifying, no x's left over. That indeed is my horizontal asymptote. For the next one, did you put y equals 0? If so, you are correct. Or if I take the highest power on the bottom, which is an x cubed, and imagine that the highest power in the top is also an x cubed, but there are 0 of them, and simplifying, we get 0. That is, the horizontal asymptote is y equals 0.